Hello, welcome back. This is Dr. Oz from Western Kentucky University. Today we're going to try to solve a differential equation by using the integration techniques that we learned so far. And here the differential equation is dy over dx to be equal to x minus 2 divided by x. And once you try to write the general solution is going to depend on an arbitrary constant, because that's what we do in integrals, right? Once we integrate a function, then the result is the antiderivative of that function plus an integration constant, and that integration constant can be anything, any number. Well, since solving a differential equation is in fact doing integration, then we're going to have an arbitrary constant coming along with the antiderivative. So that would tell us that we have infinitely many solutions, but the question is asking to graph at least like 3 solutions, and then one of which should pass through the given point 1 and 0. So we're going to, in fact, look for the solution passing through 1 and 0. Indeed, we're going to find a particular solution that passes through the point 1 and 0 out of infinitely many solutions. Okay, so what is the meaning of this differential equation? Well, we are looking for a function y whose first derivative is x minus 2 divided by x. It's equivalent to say that y should be the antiderivative of x minus 2 divided by x. We may have more complicated differential equations in the future to work with, but this one is specifically dy over dx equals a function. So who is y? Well, y is the antiderivative of this given function. So the next task that we're responsible for is to integrate this quantity here. So, and you may use u substitution or any other techniques that we learned, but I think the best strategy to apply here is to split the fraction into 2 pieces. Okay, so why don't we write this as like x over x minus 2 over x. Then this would allow us to integrate each piece separately, because we just use divide and conquer type technique, right? And x over x is just 1 minus 2 over x dx. All right, in that regard, 1 has the antiderivative x, and then 1 over x, because of the log rule that we learned in this section, that the integral of 1 over x is ln absolute value of x, and 2 is just a multiple, so I just sort of like carry that forward. And then we don't forget to add an integration constant. The antiderivative, in other words, the antiderivative of dy over dx is y, and y is equal to x minus 2 ln absolute value of x plus c. We can perfectly go ahead and then choose certain c's to graph this function, but let me just finish this question and then find that particular curve that passes through 1 and 0. So in other words, I'm looking for a solution where x equals 1 and y equals 0. All right, why don't we just consider that solution? Y equals 0, x equals 1, and 2 ln 1 plus c. So in fact, this allows us to determine the arbitrary constant explicitly, and ln 1 is 0 by the property of ln. So then c plus 1, or 1 plus c equals 0. That implies that c equals -1. And out of infinitely many solutions here, the particular solution, let me call this y particular, the one that passes through 1 and 0, is exactly equal to x minus 2 ln x, and c is -1 minus 1. Okay? So in fact, the general solution of this differential equation is the one that contains c, and the one that passes through 1 and 0 out of infinitely many solutions in the form of the general solution is the one that comes with the arbitrary constant to be exactly equal to -1. All right, this is the graphical outlook of the general solution for particular choices of arbitrary constants. So in one case you have -3, and in another case you have c to be equal to -2, -1, 0, 1, 2, and 3. In fact, the question was asking to plot only 3 of them, but I just wanted to show you like a good spectrum of solutions for different choices of c's. And in particular, the third one, as you see, the green plot here is the one that corresponds to the particular solution, which was in fact the curve passing through the intercept 1 and 0, x-intercept 1 and 0. The green one is the only one that passes through 1 and 0. And here I used the logarithmic notation here, but in fact, when I say that, it's like logarithm coming with base e, but in fact this is ln of x, so don't get confused based on the description of the function here. It's essentially ln of x here, so you can actually replace those by ln x. Alright, this is the end of the video. Thanks for watching. I'll see you in another video. Bye.